Okay, let's dive into this explainer and look at what has to be the ultimate cosmic paradox. I mean, think about the sheer uncountable variety in our cosmos, right? We've got stars, planets, swirling nebulas, us, but then you have the most massive, terrifying objects of them all, black holes. And the crazy thing is, they break absolutely every rule of complexity. Today, we're going to explore the three-number paradox. We're going to uncover how these mysterious, destructive forces strip away the universe's information and what that actually tells us about the very fabric of reality itself.
Now, what's really staggering to think about is the immense contrast between a basic celestial body and a mammoth black hole. Take our moon, for example. To accurately describe it, you literally need millions of data points. You've got the latitude, longitude, and size of thousands of different asteroid craters that have built up over billions of years. You need its surface chemical composition and how that chemistry varies from region to region. That's millions of numbers just to describe our simple, relatively small moon. But then, to describe the most massive, destructive single object in the entire universe, a black hole, you only need 3 numbers. That's it. Just 3.
So here is the crucial, absolute kicker. No matter how a black hole actually forms, it can be entirely defined by just 3 parameters: mass, electric charge, and angular momentum. It doesn't matter if it swallowed up gas and dust over billions of years, or if it formed from the direct collapse of a supermassive star in a supernova, or even if it's smashed together with other black holes. None of that history matters. Those 3 numbers give you absolutely everything you need to know about it. Right, so this immediately begs a massive cosmic detective question. If you took every encyclopedia on Earth, every electronic data bank, literally every single number ever thought or said by anyone, and you just threw all of that into a newly forming black hole, how does it strip all of that incredible detail down to just 3 numbers? Has the black hole simply forgotten its origins, or does all that vast information actually survive in some hidden, invisible form?
Let's actually rewind a bit and trace the historical trail, because this paradox has really been centuries in the making. Way back in the 1780s, an English country priest named John Mitchell realized that if a star was dense enough, its gravitational escape velocity would exceed the speed of light, creating what he called a dark star. Then skip to 1915. Astronomer Carl Schwarzschild, literally seeking a mental escape from the hell of the World War I trenches, calculated the exact critical radius where a mass forms a strict point of no return. And by 1963, Roy Kerr expanded this exact math to spinning black holes, which behave a lot like a supermassive cosmic ballerina pulling her arms in until she collapses.
Schwarzschild's brilliant mathematical solution proved that if mass gets dense enough, it creates a boundary that traps absolutely everything, even light. This is the event horizon. To put this into a crazy perspective, the Schwarzschild radius for our sun is about 3 kilometers. If you wanted to compress a human being down into a black hole, you would have to shrink them to a radius smaller than the nucleus of an atom. But once matter crosses this boundary, the standard laws of classical physics completely break down and everything is pulled inevitably toward the central singularity.
And this brings us right back to how physicists proved the uniqueness theorem. It essentially whittles down those endless, messy, celestial variations into 3 strict properties. Every single black hole in the universe is tightly constrained by its mass, which physically deforms the curvature of space-time, its electric charge, and its angular momentum, which is just the rate of its spinning axis.
There's actually a famous, kind of playful quote by American physicist John Wheeler that perfectly encapsulates this sheer mathematical simplicity. He said, "Black holes have no hair." And what he meant by that is they shed all their messy, complicated historical hair once they form. You know, an asteroid has its unique pockmarks and birthmarks. A star has its specific elemental makeup. But a black hole, it is completely bald. It's just mass, spin, and charge.
Okay, so everything seems perfectly neat and simple, right? Well, not quite. Just when we think we have it figured out, thermodynamics throws a massive wrench into our understanding. We all intuitively know that standard hot objects, like a roaring campfire, cool down to a glowing ash as they lose energy. But black holes? They actually operate completely backwards. A black hole gets hotter as it loses energy, eventually evaporating in a blinding blaze of radiation. To really grasp why they operate backwards, we have to talk about entropy. Entropy basically measures the number of internal microscopic configurations in a system. Essentially, it's hidden messiness. As physicist Arthur Eddington famously stated, the law that entropy always increases holds the supreme position among the laws of physics. So if you mix hot tea with cold tea, the universe's overall entropy goes up. But what if you throw that mixed cup of tea straight into a perfectly smooth, bald black hole? Does the black hole just delete that entropy and violate the supreme law of physics?
Well, physicists Jacob Bekenstein and Stephen Hawking tackled this exact problem, and they doubled down on the complication. They proved that black holes are absolutely not cold, zero-temperature voids. When that cup of tea falls in, its entropy is actually transferred to the black hole. It turns out, black holes hide a vast internal cornucopia of microscopic configurations, meaning they must have a calculable temperature. For instance, if you had a miniature black hole the mass of Mount Everest, it would burn at hundreds of billions of degrees.
Which leads us to probably Hawking's most famous and enduring discovery. Because black holes have a temperature, they aren't completely black. They actually emit a featureless thermal glow known as Hawking radiation. This happens right at the edge of the event horizon, all thanks to quantum physics. Because of Heisenberg's uncertainty principle, particle and antiparticle pairs are constantly popping into existence in the vacuum of space. If this happens exactly on the edge of the event horizon, the pair splits. One particle gets sucked into the black hole, and the other escapes into space, carrying a tiny, tiny bit of energy away with it.
But wait, this setup leads us straight into a terrifying physics nightmare called the information paradox. Let's walk through it. Step 1. A highly detailed encyclopedia falls into a black hole. Step 2. The black hole pulls it down, and its physical form is utterly crushed at the central singularity. Step 3. Over trillions of years, the black hole slowly leaks energy through Hawking radiation and evaporates entirely into a gas of completely featureless thermal particles.
And here is our ultimate, universe-breaking cliffhanger. If the black hole completely evaporates into featureless radiation, what in the world happened to the unique details of that destroyed encyclopedia? Did the universe just permanently hit delete on that information? Because that completely violates a fundamental rule of quantum mechanics. Information literally cannot simply be lost from the universe.
The crucial clue to getting out of this massive paradox came directly from Hawking's own entropy formula, which revealed an incredibly strange geometric fact. Think about a balloon filled with gas. The entropy, the number of ways the molecules can be arranged inside, grows with the 3D volume of that balloon. But a black hole's entropy doesn't grow with its 3D volume. It grows exclusively with the 2D surface area of its event horizon.
Now hold on to your hats, because what this implies is a truly mind-blowing twist. Because the entropy is tied to the 2D surface area, it suggests all that lost information from our encyclopedia isn't actually swallowed into the 3D void at the center of the black hole. Instead, it is essentially painted onto the lower dimensional event horizon boundary. This is the holographic principle. It's the wild idea that the internal physics of a system are entirely encoded on the surface, just like a flat 2D hologram contains all the visual information of a 3D image.
This specific principle allowed physicists to do something incredible, a breakthrough known as the ADS-CFT correspondence. It basically acts like a mathematical universal translator. It lets scientists perfectly translate messy, information-destroying gravity problems, where things get crushed in singularities, into clean, lower-dimensional quantum math, where absolutely nothing is lost. It proves mathematically that a gravitational system in a specific number of dimensions is identical to a non-gravitational quantum system in one less dimension.
And get this, mathematicians actually put this crazy concept to the test, and the math worked. In 1995, physicists Andrew Strominger and Qumran Vafa peered inside ideal, theoretical 5D black holes using string theory. Now, while they couldn't test real-world astrophysical black holes just yet, they calculated the exact internal quantum microconfigurations using complex mathematical structures called branes, spelled B-R-A-N-E-S. And remarkably, their exact count of these microscopic states matched Stephen Hawking's macroscopic area-based entropy calculation perfectly.
So, to wrap up this explainer, let's look at where we started. We started with the simple three-number paradox, realizing that black holes swallow the universe's complexity and seemingly paint it flat onto a two-dimensional surface. But this leaves us with a truly mind-bending final thought. If the profound secrets of gravity and quantum mechanics mean that a black hole's 3D interior is actually just a holographic reflection of its 2D boundary, what if the true reality of everything around us, our entire 3D universe, what if it is actually just playing out on some distant, lower-dimensional boundary? It is a question that literally keeps the greatest minds in physics awake at night, and honestly, I hope it sparks your curiosity too. Thanks for joining me on this deep dive.
Welcome to The Explainer. Okay, let's dive right into this. Today, we're taking a mind-bending journey into the most mysterious, absolutely physics-breaking objects in the entire cosmos, black holes. We're going to explore how these cosmic monsters forced physicists to question the very fabric of reality, culminating in something called the information paradox.
It is a true scientific mystery, and to really grasp it, we have to start by looking at how we measure the universe.
You know, think about what it actually takes to describe a simple moon. It's pockmarked with craters from billions of years of asteroid impacts. Just to map out those craters, you'd need thousands of coordinates, latitudes, longitudes, sizes. Then you have to add the chemical composition of the surface in all those different regions. Very quickly, you need millions of numbers just to describe a basic moon. Now compare that to the most massive, destructive single object in the universe, a black hole. How many numbers do you think it takes to describe it?
The answer is shockingly simple. 3. That's it. Literally just 3 numbers. You could take every encyclopedia, every electronic databank, every star, planet, and speck of dust in our galaxy, and collapse the whole shebang into a black hole, and all of that uncountable information is completely wiped away and reduced to just 3 digits.
So what are those 3 digits? What's incredibly profound is how perfectly they define this uniqueness theorem, also known as the no-hair theorem. Those 3 parameters are mass, electric charge, and angular momentum, which is basically its spin. If you know these 3 numbers, you know absolutely everything there is to know about that black hole. How it was made, what went into it, all of that becomes entirely irrelevant to anyone observing from the outside.
John Wheeler, the brilliant American physicist, actually summarized this perfectly with a famous, kind of funny catchphrase: "Black holes have no hair." And by hair, he meant all those extra distinguishing details, the unique bumps, the chemical makeups, and the historical records that normal objects have. Black holes are completely bald. But as you can imagine, this immediately sets up a massive problem. Where does all the other information go? Does the black hole just forget its origins? Well, to solve this, we need to quickly look back at how we discovered these monsters in the first place.
Let's rewind a bit. In the 1780s, using Newtonian physics, an English priest named John Michell realized something crazy. If a star was dense enough, its escape velocity would exceed the speed of light, creating a dark star. Fast forward to 1915. While literally dodging artillery in the miserable trenches of World War I, astronomer Carl Schwarzschild found the first exact solution to Einstein's brand new equations of general relativity, proving Mitchell's idea mathematically. Then, in 1963, Roy Kerr expanded on this to describe spinning black holes. Picture a cosmic ballerina collapsing inward.
Schwarzschild's math revealed something honestly pretty terrifying, a critical distance known as the event horizon. Think of this as the ultimate point of no return. The laws of physics dictate that nothing can move faster than light, right? So if light cannot escape this boundary, nothing can. Once an astronaut crosses the event horizon, time itself fundamentally changes. It no longer points to the future. It points exclusively inward, toward the very center, the singularity. It's an inescapable fate.
Okay, so the crucial point here is what happens to the stuff that actually falls in? In the early 1970s, a physicist named Jacob Bekenstein was discussing this with John Wheeler, and he came up with a bizarre thought experiment. Imagine mixing a cup of hot and cold tea. By doing this, you increase the universe's entropy, its overall disorder. But what if you throw that mixed cup of tea straight into a black hole? Does all that entropy, all that information about the mixed tea just vanish entirely?
Now, this thought experiment was incredibly dangerous to physics. The second law of thermodynamics states that the total entropy of the universe must always increase over time. It is the supreme rule of nature. But if a black hole swallows matter and just resets to 3 simple numbers, it's effectively erasing entropy from the universe. It looked like black holes were straight up breaking the ultimate law of physics.
And this is where Bekenstein and later Stephen Hawking made a massive breakthrough. They realized the only way to save physics was to conclude that black holes do, in fact, possess entropy. They aren't just empty, dead voids. They must hide a massive number of internal microconfigurations. And in thermodynamics, there's a hard rule. If an object has entropy, it must also have a measurable temperature.
But here's the really counterintuitive part about black hole temperature. Ultramassive black holes, we're talking the billion solar mass giants at the centers of galaxies, are actually freezing cold, just a billionth of a degree above absolute zero. But tiny, micro black holes, roughly the mass of Mount Everest, they'd be burning incredibly hot, at hundreds of billions of degrees. Strangely, unlike a normal fire that cools down as it burns out, a black hole actually gets hotter as it loses energy.
Wait a second, how can a black hole emit heat if literally nothing can escape its gravity? Let's walk through this step by step, because it's fascinating. It all comes down to Heisenberg's uncertainty principle right at the event horizon.
Empty space isn't actually empty. The quantum vacuum is constantly borrowing energy to instantly form particle and antiparticle pairs that usually annihilate each other right away. But right on the razor's edge of the event horizon, one particle falls into the abyss and the other escapes into deep space. Because energy cannot just be created from nothing, the black hole itself must repay that borrowed energy by losing a tiny, tiny fraction of its own mass.
That escaping particle is what we now call Hawking radiation. It was Stephen Hawking's most enduring contribution to science. He proved that black holes are not completely black. They glow, they emit thermal radiation, and because they're losing mass to pay for this radiation, given enough time, a black hole will completely evaporate in a final blinding blaze of energy.
Which brings us right to the ultimate true crime mystery of astrophysics, the information paradox. If a black hole eventually evaporates into nothing, leaving behind only random, featureless thermal radiation, what happened to the unique information of the stars, the planets, and the encyclopedias that fell into it? According to Hawking's initial math, the radiation contains zero trace of what made the black hole. So, was that information truly destroyed forever?
Well, the clue to unlocking this mystery was hiding in how we measure entropy. Think about a balloon full of gas. The amount of entropy, the number of ways you can arrange the atoms inside, is proportional to the 3D volume of the balloon. Makes sense, right? But for a black hole, Hawking and Bekenstein's math showed that its entropy didn't scale with its 3D volume at all. It scaled exclusively with the 2D surface area of its event horizon.
This odd little mathematical quirk gave birth to one of the most awe-inspiring ideas in modern physics, the holographic principle. This is the mind-bending theory that the physics of a 3D gravitational system can be entirely, perfectly encoded on its 2D boundary. Imagine counting all the internal configurations of a black hole, not by looking into its deep, dark center, but by splitting its surface, the event horizon, into tiny digital blocks of ones and zeros.
This quirky mathematical realization gives us the solution to our paradox, often known as the ADS-CFT correspondence. The interior of the black hole, with its crushing gravity and singularity, is essentially just a translation of a flat 2D quantum boundary that has no gravity at all. Therefore, the information of those encyclopedias was never actually lost inside a 3D space. It was perfectly preserved, encoded like a hologram on the 2D surface of the event horizon. When the black hole evaporates, that data is carried away in incredibly subtle quantum correlations hidden right within the Hawking radiation.
And we actually have mathematical proof of this, albeit in theoretical models. In 1995, physicists Andrew Stringinger and Kumran Vafa looked at a highly specific mathematical 5-dimensional black hole using string theory. By counting the internal microstates on its lower dimensional boundary, they arrived at an answer that precisely matched Stephen Hawking's original entropy calculation. The math actually works. The information survives on the boundary.
So what's the big takeaway here? It's honestly profound. Black holes, by testing the absolute limits of gravity and quantum mechanics, have shown us that a 3-dimensional space can just be a projection of a 2-dimensional boundary. Which leaves us with the ultimate question. If the complex 3D interior of a black hole is really just a hologram of its 2D surface, is our entire 3D universe just a hologram projected from some distant 2-dimensional boundary? It's a staggering thought, and one that proves nothing in the cosmos is quite as illuminating as the dark heart of a black hole.